Okay, so now we're going to spend a little bit of time talking about resistors as sensors, and we're also going to introduce an ammeter. So, okay, what have we got here with this blinking LED, or rather this shining LED, I should say?
Yeah, the LED is lit, and it's the exact same circuit that we've been working with before, and that we changed the values of this resistor, and we showed that as we vary the current going through the LED, we can change its brightness. And so the brightness of the LED is sort of a proxy, a way that we can understand roughly how much current is flowing through the circuit.
Okay, so that's the circuit we've been messing with the whole time. And then next to it are a series of other resistors that each do something different, and we'll come back to those in a minute. But the first thing we're going to do prior to messing with those is we're going to remove the LED and substitute it with something that instead of reporting the current going through it as kind of a light level, actually measures the current. Okay, so let's go ahead and do that. I'm going to yank this LED out.
Okay.
And you're going to put in two wires exactly where the two terminals of the LED are.
Exactly where the LED went, and this is the ammeter that I'm hooking up.
Okay.
The meter that measures current.
So Tom's about to show you where this is going, but what's going on here is current is going up through one of the wires and down into the MIDAC. We'll show you how it's connected in a second, and then back around through the circuit. Okay, so why don't we take a look real quick just how that's connected.
Okay, so if I bring my MIDAC into frame, you can see that I have the red wire plugged into the ammeter, or the current measurement port. It's very important that it's not plugged into the voltmeter port, because they're different. We'll get to that later, but for now, make sure, since we're measuring current, put it in there, and then I, of course, have the black lead going into common.
Perfect. And as soon as you did that, I noticed you got about 8.5 milliamps, which is the current that's set by that voltage and that resistance value. You should be able to calculate that for yourself from Ohm's law. Okay, that's great. The thing to point out for the moment, and as Tom said, we'll come back to all this later in the course, but the ammeter is doing two things. One is it's letting current flow through it, and as that current flows through it, it measures the amount of current and reports it. But the other thing is that as it does this, it doesn't generate an appreciable voltage across the two terminals. If it was an ideal ammeter, there would be absolutely no voltage difference when current was flowing through it. It would be like the resistance was zero. That would be perfect, because it wouldn't bother, it wouldn't disturb anything. But real ammeters have a very tiny amount, and we'll come back and talk a little bit about how this matters to circuits as we delve into the course.
Okay, great.
Okay, so now we've got all these other resistors, 4 of them, in fact, variable resistors. So let's start talking about them. While Tom moves the first one, I'll talk about it. So the first one is a potentiometer, and you'll notice it's got 3 leads, but we're only using 2 of them, and it's got a knob. And the first thing you'll notice is if I use my fingers just to turn this little knob, you can see that the current is changing. So let me go all the way one direction, and then I'll go all the way to the other direction, and kind of leave it there for now. There we go. Okay. So we're only using 2 of the terminals. So do you know why?
Yeah, because if you look at the potentiometer, if you were able to cut it open and look inside, you'd see sort of a long resistor, actually, going from the outer 2 terminals, between the outer 2 terminals. And the knob is controlling the 3rd middle terminal. And it's actually a wiper that's choosing where, it's actually dividing that long resistor into 2 resistances. So we get part of the resistor divided over here and the other part over here that we can measure.
So between the 2 outer terminals, the resistance is always fixed, and the knob controls where the middle one touches, and so the resistance between the middle terminal and any of the other 2 changes. And so that's why with potentiometers, we generally only ever tap off of 2 of the terminals, and as I change the knob, that particular variable resistance will change.
Yeah, and if you think about our expression for resistance, what we're doing is we're modifying the length of the resistor.
That makes sense. Okay, so the material is staying the same, but it's the length that we're changing by changing kind of this little wiper contact. Okay, cool. So that's a pot, or a potentiometer. Why don't you move on to the next one?
All right. So the next resistor is a thermistor.
Great. So while you wire it up, so a thermistor is, you can kind of guess from the name, it's a resistor whose resistance changes with temperature. So I'm going to use my finger. So you'll see there we've got some current, and as I hold it down, look at that. It's changing as the resistance changes. Okay? So the first thing I want you to think about before we talk a little bit about it is you should be able to calculate what that resistance is, just like you should have been able to for the potentiometer, based on the fact that you know that the battery voltage is about 9 volts, and you know that the current going through this thing is about 0.97 milliamps. So how do you think a thermistor works?
Okay, well, if we look at our formula for resistance, we must be modifying, as we modify the temperature, we have to be changing the resistivity of the material. So that rho must be changing as a function of temperature.
That's right. For this kind of thermistor, absolutely right. The geometry is more or less constant, but it's the material itself, the resistivity. And the material is chosen. These materials are chosen to have what's called high temperature coefficient. So they'll change a lot. The resistivity will change relatively a lot with temperature. OK, the next one is a photocell. So that's a resistor whose resistance changes with the amount of light incident upon it. And so there you see you get a current. Again, you should be able to calculate what this resistance is and check to see if it matches. And look at that. All right, I put my finger, I'm changing the amount of light. So this is, it could be like a simple little light detector eye. And in fact, lots of robotic projects have these little photocells to detect light and dark. And so the last one we're actually going to use in our robot. That one, while Tom hooks it up, is a flex sort of a flex sensor, okay? So it's a resistor that's going to change if I bend on it. And this was used actually in some game consoles, gloves, in fact. So you can see, look at that. I'm bending it, and the current is changing. Again, you should be able to calculate this. As a rough estimate, it's about 100K. I think, if my memory holds, it's about 100K in one condition, about 10K in the other. Bent fully and straight.
So it would detect if your finger were bending, if that resistor
That's
were
right,
on
yeah,
the
it was
finger.
used in gloves. It was used in gloves when you had these sort of console gloves. But what we're going to do with it now is use it to motivate a very important circuit called the Wheatstone bridge, and that's going to be the first thing we put into our robot.